This is section 6.5. What we're going to do here, it is focusing on means or averages. The only thing is rather than doing a group comparison, the way that we've been doing in earlier chapters, like chapter 4, chapter 5, or in more recently in 6.4, where you had, a mu one versus like a mu two, they're going to change things up. And what they're going to do instead is they're going to focus on the averages of individual pairings. So here, let's start looking at an example, and you'll start to see what I mean. So there's going to be the difference between responses for each case, which we're going to call that a pairing. So what I want you to imagine is that, rather than there being, how did everybody in here in this class do versus everybody like in this class, like who scored higher grades than the other class, and you would do like an average versus an average. What they're doing instead now is they're not comparing a big group to another big group. What they're doing is seeing what effect some treatment had on each individual. So there would be like you, and then they would see how you did later on. And then they would also take another person. How did they do? What was their like score at the beginning? And then how did they do later on? And then they're going to average out each difference. Like, let's say you in a class like grew 15 points and someone else grew by, 8 points. And then someone else grew by like, 1 point, but there's variation among there. So that's what they're going to do here is like see how did everybody individually progress from the beginning to the later part of the study. So that's the idea of like pairings. So each unit is compared to itself. Now there are also versions of this where you could do like pairings from like one person to someone else in another class, uh, contingent that they're equivalent comparisons. But in the examples we're going to do, it's going to be a lot of, this individual is being compared to themselves. So like a snapshot of before and after. And the reason why you want to do this is because not everybody's the same. Think about like a math class of like 30 students. Some students might come in where maybe it's been a while since they've been in a math class. And so for them, the amount of change or growth could be significant, right? They over 16 weeks or over 12 weeks, they grow a lot in how much that they learn versus somebody who comes into the class who maybe they were like in some AP math class. And so for them, it's like, well, they're already kind of know a lot of stuff. And the amount of growth that they experience is just a nudge. That doesn't necessarily mean anything bad. It's just they didn't have much room to grow. So for that reason, it's nice to do pairwise comparisons so that each individual, how much they grew versus how much someone else like barely grew or maybe medium sized growth, you capture all those individual like experiences rather than just throw them into like one big giant group and they get blurred with everyone else. So if there's variation from person to person or pairing to pairing, it's a good idea to do matched pairs. What it does do is help decrease a lot of your standard error so that you're able to detect differences as opposed to not pairing things up. So here's what I mean. This is the last little bullet point is whenever you do matched pairs, you might end up getting a significant result, like a small p-value that says, hey, this thing you were testing was effective. When if you don't do matched pairs where you just do like everybody in group one versus everybody in group two, it doesn't. Again, because a lot of sort of the individual growths might get blurred in with those who maybe didn't see very much growth, and so you lose a lot of the those little details. Now let's look at an example where things were done in a matched pairs. So in the Olympics, this was in 2008, there was some controversy over a new wetsuit that was being used by some of the athletes, and some felt that it was giving an unfair advantage to those who owned it and were using it as opposed to those who did it. Now, when you think about like the Olympics, swimming, if even if you're just a thousandth of a second faster, that doesn't sound like much, but in the Olympics, yeah, it could be the difference between like silver versus gold, or getting a medal or not getting a medal. So it's a big deal if it's making you even just what appears to be only fractions of a second faster. So in this case, what they did is they wanted to put it to a test, to see whether it is on average making swimmers faster. And so for their participants, they got 12 athletes, but from different perspectives of swimming. Some of them were male, some of them were female, some of them were more like your like all about like speed type of events, and some of them were more like your endurance. But they wanted to check to see is it making them faster whenever they put the wetsuit on. So when you look at this here, just looking at person number one, you can see that when they were wearing the wetsuit, a higher number means they were faster. So with the wetsuit, they were moving at a speed of 1.57, which is just a little bit faster than when they had no wetsuit. Specifically, 0.08 is how much faster they were with it. Then if you look at the second swimmer, same thing. Think of this as sort of like how much boost they got. They were going a little bit that much faster with the wetsuit. And for every single swimmer across the board, everybody experienced an extra little oomph in their speed whenever they had the wetsuit. Yeah, you can see every single number here is higher in terms of how much faster they were going as opposed to the second row without the wetsuit. So the observation or the little comment that I want to make right here is that each swimmer was faster with the wetsuit. Now, what some might say is case closed. Yeah, like it is making swimmers faster, and for those who can't afford it or have access to it, that's not going to be fair. But again, why do we do hypothesis tests? To see whether this was a fluke or not, right? To give a measurement of it having been a fluke or not. And then also the reason why we do confidence intervals is to see whether zero is plausible or not. Now, the last little part before we actually go further into the example is, whenever you do match pairings, it's a good idea to do it whenever this is the situation where you're comparing male to female, you're comparing competitive to like triathletes. And so, since we're going to expect that they're not all going to perform similarly, it's a good idea to just focus on you versus you versus yourself. Let's not compare you to other individuals who are doing, different types of events or um, performances, just things in general are going to make them different. So by doing match pairings, what you're doing is you're eliminating um, the deviation that is comparing across different types of swimmers. And instead, you're just focusing in on you as an individual. Like, how did you do? How did you do? All right. Now, here's what's happening as we go into the actual doing something with this example is they have taken this right here, which is the differences, like how much faster each of them was with the wetsuit, and that's what's going to get analyzed. That's what's living here now. It's the average, it's the differences for each of them with the wetsuit on. And that's what we're going to average out. And so let's go ahead and just do that to get started. It says give notation and calculate the mean of these sample differences. And so here's what the notation is going to be. It's the sample mean. Okay, we've seen this before, but it's the average of the differences. And that's what the little d is there for. It's the differences for each of them, and we're averaging them up. This was just a sample. So go with your calculator and add all of those up and then divide by 12. Again, you could pause the video if you want to do that first before I give it away. but it should come out to be, when you do it, just check to make sure you get that by adding up all the numbers, dividing by 12. You should get 0.93 as the total. When you add them all up, divided by 12. And that's going to be what we call today our statistic, the average of the differences. So yeah, so this right here is the average. This is the average amount of extra speed that they all had with the wetsuit. Now, the other thing, and that's all this up here is, like just the notations that we're going to be doing. Really all it is just adding a little, like we've seen X bar, we've seen S, we've seen N. All they're doing now is doing a little D to suggest we're focusing on the differences for each person. Use stack key, one quantitative variable to calculate the standard deviation of the sample differences. Okay, so here's what's happening. In section 6.2 is when we talked about doing the standard deviation for a single mean, and it involves standard deviation. The thing is we don't have that right now, and it's usually a little bit more involved formula, but we're going to have StatKey do it for us. So what I'm going to do here is I'm going to stop sharing on this screen just because I need to type some stuff. But look at these numbers. 0.08, 0.10, 0.07. We want to put those into StatKey so that it can do the standard deviation for us. So, and that's all I'm going to do. I'm going to take these 0.08, 0.10, 0.07, all the way up to 0.05 and 0.10, every single one of them, and put it into StatKey. And let me show you real quick with this computer where it's at. So they're telling us to go right there where it says one quantitative variable. And then we can put in our specific data. Right now it's got, some data set about like temperature. But right here where it says edit the data, that's where you're going to put it. And so here, let me stop sharing so that I can go to my other, because right now I'm on my iPad and I want to show you more efficiently with just typing over here. So I'm going to share my screen on this one. And right here, going into StatKey, you're going to go to the one quantitative variable. And then right there at the edit data, all I want to do is just clear this all out. We don't need it. And we also are not going to need any kind of like special like labels for like what this information is. We just purely want to put the numbers in there. And so at the very top, once you've deleted everything, you'll put in the very first number. That was the difference for the first swimmer, and just hit enter. And then 0.10 was the next person. And then the third swimmer, the fourth swimmer, and so on. So you'll need to do this on your homework for once or twice. I can't remember immediately, but I know it's going to need to happen where in order to get the standard deviation, there is a formula for it, but in our class, we're not required to have to use the formula for calculating standard deviation. We're just going to let StatKey do it for us. And before I hit enter or OK, I'm just real quick checking to make sure I didn't miss any numbers, and I think I did right here. Yeah, let me real quick spot check it. 08, 10, 7, 8, 10, 11, 05, 05, 06, 08, 05, and 10. Let me just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So once you've got them in there, again, all I did was hit enter to make like a little column of the values. And now I can click OK. And again, turn these off because we don't have any sort of like name for like what this data is. It's just purely the numbers. And we'll click OK. And then right over here, you'll see, yeah, that's the standard deviation there. 0.022. Again, thank you, Stacky, for doing whatever formula that you did in order to get that for us. Yeah. Okay. All right. So I'm going to stop sharing there. And again, you'll need to do that another time, uh, once or twice on the homework. And you don't have to, if it says to include it, I mean, I can't remember if on the homework it says that you need to upload your like screenshot of that. I really feel like I don't need to see that. It's basically just you using a calculator. So part of me is like, if you don't upload that little stat key of the standard deviation, that's okay. All right. So now just going back to sharing here on my iPad. Actually, I'm done with this. Let me go. I don't need that. I need just back to the lecture. So based on Stacky, the standard deviation for the differences. So standard deviation of the differences would be notation S subscript D. And then Stacky found out that it was 0.022. Sample size, sample size of the differences is going to be 12. Again, because that was 12 swimmers. So you might put the word pairings here. Now, what this is building up to is eventually to do a hypothesis test. So they want us to test to see whether the wetsuits make a difference. In other words, test whether the average difference differs from zero. So we're going to have a null, we're going to have an alternative, and this is what we're going to do. The average difference. So it's going to be the average or the mu for all swimmers and the little d for differences. And then because I said differs, it's going to be a two-tail, whether it differs from zero or whether it equals zero. Now, for section 6.5, this is always 100% going to be the notation that you use for the null hypothesis, which right now, what I have circled there would be saying that the average difference whenever someone wears the wetsuit versus whenever they don't is zero, meaning the wetsuits don't make you faster, which according to the sample of the 12 swimmers shows that no, it does. So that right now I'm pretty sure we're going to get a nice rejection once we get the p-value. Now it is two-tailed. We'll just make a little note. So whenever we get to the p-value, we'll do, times two. But for the standard error, the formula is up there at the top of the page. It's that you take the standard deviation of the differences and you do the square root of the sample size. So again, we wouldn't be able to do this if we hadn't gone to Stacky to find out that the standard deviation of the differences was 0.022. We know that it's square root of 12 swimmers. Again, we used this formula already in 6.2. It's coming back also to help us with this section as well. We got 0.006 as our SE. And then for F, what we're doing here is trying to standardize to see whether we have something that's extreme or not. So that it's up there at the top, but it's your statistic minus the null over SE if I want to just put it back into just the way that we usually have been writing it in 6.2 and 6.4, or even in even starting with like chapter 5, statistic minus the null over the SE. Our statistic is this guy. All right, that was the average difference. 0.0775 minus the null value 0, that the wetsuits make no difference. And then our SE is the 0.006. 0.006, and then go ahead and put that in your calculator, and you should get something extreme. Now, again, remember, loosely for the normal distribution, we can still kind of tentatively use something kind of like anything more than two-ish is going to be considered extreme. But you should get 12.9. Now look what G is. G is wanting us to get the p-value. Like, do we get a small enough p-value to be able to reject the null hypothesis, which right now seems absurd that the wetsuits don't make any difference. We can see that it did make a difference for all 12 swimmers. So what we're going to need is the degree of freedom, which would be 12 minus 1, which gives us 11. And then we've got our t-test statistic, and then we also know that it's two-tail. So let's go to the t-distribution, right? Again, remember, the reason why we use the t-distribution is anytime we've got a sample size that is on the smaller side, like less than 30, let's go to the t-distribution for this. So degree of freedom is 11. And since we're doing a two-tail, let's go ahead and click two-tail. And then down at the bottom is where we need to put our 12.9, which makes sense to put it down here where the positive values are. So where you see my 2.201, click on that, and that's where you're going to put your 12.9. 12.9. Click OK. Yeah, and this is not the first time we've seen this. Yeah, that right there, scientific notation is telling us that we have a super, 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 super small p-value. That would be like 0.0000000. Right, a bunch of zeros and then 2.8. Now, I'm going to go ahead and put that in the notes, but when you see the answer key, you're probably just going to see 0. Okay, now don't let that freak you out, right? Always look back at the lecture notes. 2.8 e to the negative 8 is really just saying, like, essentially 0. Now, it would be a bunch of zeros with like 2.8 if we were to turn it to standard form. And then, yeah, we wouldn't want to forget to multiply by 2. Actually, for this one, it doesn't really matter if we forget to multiply by 2, since essentially this is still just a p-value of 0. Now, I'm going to write it just in case anyone's like, wait, what do you mean that it's just 0? Yeah, if you were to take 2.8 e to the negative 8 and you were to switch it into standard form, it's saying to move your decimal 1, 2, 3, 4, 5, 6, 7, 8 times to the left. So it'd be like point, yeah, 7 zeros to 8. But again, I'm just saying that it's not worth us writing all that out. Just call it 0. Okay. So now we know already, since the p-value is really, really small, at an alpha of 1%, we would be able to reject the null hypothesis and also state. Now, this one, usually in some of the previous sections, these are both separated in two different parts, but now they're going to be joined together. But you want to make sure that you mention both. Reject the null hypothesis. That's our formal generic conclusion. And because the p-value is so small, that's giving us strong evidence to suggest the wetsuits make a difference. Or you could say that the mean difference is not 0. Just something to tie it back into the context. That's what the whole controversy was about, is whether the wetsuits are making these swimmers faster. Yeah, so they do. They make a difference. And so that's the end of that hypothesis test. What we're going to do now is we're going to see, well, how much faster? If zero is not plausible, then and they do make the swimmers faster, like how much faster do they make swimmers? So as we go on to this next page of the notes, I want you to know it's a continuation in that the X bar D was 0775. The standard error that we had from the last page was 006. That was 12 swimmers, and degree of freedom was 11. And notice what they want us to do is calculate a 95% confidence interval. So here, I'm going to put it right here for how much faster it makes the swimmers. The thing is when we do our statistic plus minus T star times SE we've got, but T star we don't have. So what we'll need to do is go get that. And what we'll need is that we're doing a 95% interval and that the degree of freedom is 11. With those two ingredients, you can get your T star. Now, keep in mind, we're wanting a two-tail for this. All right, we're going to use a two-tail because we want the lower value, we want the upper value. And when we get here, I'm just going to erase this plot. The degree of freedom, since we're doing actually the same study, we can leave that as 11. And then if you click the two-tail, you'll see that it automatically defaults to the 0.95. Now, sometimes when we've done this, we needed to change it to 0.99 or 0.90, but we actually want a 95% interval. So down at the bottom is what we need. You can see that there is a 2.201. And that's what we're going to be multiplying right here to get the width of 95%. Now, the statistic, that's our sample mean of the differences. We're going to have 0.0775. Again, we're going to do a minus version, a plus version. We know that T star is 2.201. Our standard error we got from the last page. And you would calculate both of those to get your lower value, your upper value. It says to do 3 decimal places. Again, if you decide to do only 2, that's not going to hurt anything. Just don't do round it to 1 decimal place. We'll say that we are 95% confident that the average increase, and really all I'm using is their words, right? This is an interval about the average increase in velocity in meters per second whenever they're using the wetsuits. Now, hopefully you've already done the calculation, but here it comes, 0.064, 0.091. So the average increase, like how much faster it makes them whenever they're using the wetsuits, is somewhere between those two numbers. But notice that 0 is not plausible, right? Which is already what the hypothesis told us, that we can reject 0. And now the interval is also just backing that up, that it's the speed is going to be 0.064 faster, or it could be as high as 0.0091 meters per second faster. And again, I know that doesn't sound like very much, but in the world of like Olympic competition, yeah, even like the smallest little nudge of speed could be the difference between someone getting on the podium or not. All right. Now, the last thing I want to do with this lecture is is an example that is going to look uh, more representative of what to expect on the test, where um, you'll you'll need to first calculate the differences for each of the pairings. So on this one, what it was about is they were checking to see whether students' scores improved from the beginning of a statistics class as opposed to the very end. Like, did they improve? Did they learn um, as determined or represented by an exam called the CAOS, like online multiple choice test? Um, and so you can see at the beginning of the semester, this was the scores for like each of the students, and then you can see later on at the end of the course, some of them did improve. And so to calculate this, 60 we would take 60 minus 43. And so whoever student number one was grew by 17 points. Now, some of these you could probably just do mental math, like this one here. Student number two grew by 5 points. Uh, Student number three went from 48 up to 55, which would be a change of 7. Now, but keep going. Go ahead and fill out the rest of them. And again, if you need calculator to do, 80 minus 65, 85 minus 60, you're going to see that some students saw a change on the positive side. Most of them do. But then you'll also run into a couple students where like there was no change. And actually one student who for whatever reason like regressed, they went backwards. Yeah, go ahead and fill all each of those out before I do. Just give me a little bit of a head start. All right, but here they come. This one grew by 15 points. This person grew by 25 points. This one by 23. This one by 9. This is the person who seemed to go backwards. Yeah, 35 minus 38 would be a minus 3. And then we've got another positive, and then we've got a 0. Yeah, so 17, 5, 7, 15, 25, 23, 9, negative 3, 11, and 0. Now, again, this is an illustration as to like why you would maybe want to do matched pairings whenever you expect that there might be some variation or not everybody performed or grew the same, or more specifically, where some of them went backwards, some of them saw no change. Rather than like lumping them all together with like just one average for all of them, you're capturing the differences that they all each experience in analyzing those. So like each unique person and what happened to them is getting involved into the equation for the average. Which would mean what I want you to do with these is for part A is actually we already did part A. We calculated the differences, and it'll always tell you on the homework quiz test like which row to do minus which row, and it won't always be row 2 minus row 1. It could be in some situations where you're going to do the first thing minus the second. Again, just depending on the context of the study, it could change, but it'll tell you. So, what we want to do now is to go ahead and calculate the mean. So, go ahead and add all these up. Right? Add up all those values. There is going to be one where you have to do minus 3. There'll also be like a plus 0, and then divide by 10. Here, I'm going to put that right. I'll just put that right here. Again, the sample mean, but of the differences should come out to be 109, but double check this for yourself. 109 and then divide by 10 students. That's our statistic. Okay. Now, standard deviation, that's something that was not given to us. Now, um, most likely, if this does become something that you need to do on like the test, again, all the tests are always meant to be designed so that during it, you have your reference sheet, you got your calculator to do your basic calculations, but something like this that's like a stat key required thing, it would just be provided for you. Yeah. So what we're going to do is go over to stat key. And actually, I'm going to switch over to my other computer because that one's a little bit faster at me being able to type stuff in. And I'm going to go to um, yeah, right here. So we've got the I'm going to start from the beginning. Got one quantitative variable. We're going to go right into there. We're going to go to the edit data and just get rid of all this stuff. And then you can turn these boxes off because we don't have any specific like names or labels for anything. And then just start putting in the values. First person, second person, third person, all the way up to all 10 of them, including the -3 and including the 0. Sometimes students are like, oh, since it's just 0, it's not going to hurt anything. But you do need to have that in there so that it gets the representation that this was 10 different individuals. And I'm just real quick glancing at each of mine to make sure I've got all 10. And then whenever you're ready, click OK. And then again, I don't think I'm really too concerned about you like turning this in to show that you did it. I mean, if it says to do it, then go ahead and do it. But the 9.209 is the standard deviation for these 10 values. Yeah, let me go and stop sharing there. Okay, cool. And then I'm going to start sharing over here on this one again. Now, again, I can't remember if it says that you have to attach the stat key for this one. If it does, then go ahead and do it. Yeah, so you don't lose any points for not attaching this. But it's 9.219 is the standard deviation for the differences, and then the sample size. There's 10 differences or 10 pairings. Now, for these null hypothesis for section 6.5 is always going to be this. It's always going to be the average, right? The mu of the differences. That it's just 0. And the last example is that the wetsuits make no difference. And then this one would be that the test scores, there's no difference. Like whether at the beginning of the class, the end of the class, like nobody grows, nobody learns anything, which would be so sad. And then for your alternative, they're saying that the average difference at the end of the course is greater than 0, which would be a right tail test. And then for the standard error, like we did in the last example, and that's up at the top. Standard deviation over the square root of the sample size. So that's the 9.219 over the square root of 10 students. That's going to give us 2.915. Now it says use 4 decimal places, but I feel like 3 is sufficient for this one. So 4 seems a little overkill. And then we'll do our statistic minus our null over SE. Again, there's just a lot like the first example that we already did. It's going to be 10.9 minus a null value of 0 over 2.915. Again, try this for yourself, but you should get 3.74 if we keep two decimal places. And maybe finish this one without me, right? I mean, pause the video, use this and put it in the t distribution, but you're going to need to change the degree of freedom to whatever we need. Again, remember -1 from your sample size. You'll need to click left tail, right tail, two tail, whatever is appropriate for this one. Get your p-value, decide whether we can reject HO or not. There is or there's not enough evidence. But yeah, let me just be quiet and have you finish this one real quick, and then I'll finish it up with you. All right, but here it comes. So because that was 10 -1, degree of freedom would be 9. Again, we're doing right tail. So when we go to the t distribution, let's go to just clear this out. And this is from the last study. So we need to edit the parameters down to 9. Since this study only had 10 -1. And then we'll do right tail. That's not our p-value until we click on the bottom and change it to 3.74. That's our p-value, 0.0023. Now, again, that would be anytime you touch that key, that would be something to turn in just as evidence to show that you did you use the resources that we're supposed to be using. And at 1%, we can totally reject the null hypothesis and say that there is. Now, this would be perfect time to say there's strong evidence, but on the test, as long as you say that there is enough evidence, and then you give a nice little recap of what the study was about. They wanted to find evidence to support that on average, whether scores at the end of the course are greater than at the beginning of the course. So in other words, 0 is not plausible, which is great. Yeah, you don't want to be doing a course and finding out that students at the beginning, how much they learn versus on average how much they've gained at the end, that there's nothing happening, that they're just still staying at the same level of knowledge they had at the beginning than at the end, which is great, right? Students are learning. And now what we're going to do is just a continuation of this. And again, a lot of this is the same information. Everything's the same. We had 10.9 as our statistic. That was the average increase in scores. 2915 was our standard error. That was 10 students, degree of freedom 9. Now, we're going to do a confidence interval, a 95% confidence interval, but we don't have the T star. So it being that we need a 95, degree of freedom 9, let's get our T star. That's going to help us decide how much we need to multiply. Now, 9 is good. We want to leave that as our degree of freedom. I'm just going to erase the plot and switch to the two tail. That's all I did. Yeah, I just went here, reset the plot, two tail. Then there's the 95% interval in the middle. And then down at the bottom, we can see that we've got 2.262. That's what we would multiply our standard error by to get that particular width of an interval. 2.262. And then now we could take our statistic, right? And that's what this is saying here, right? This is just saying take the statistic, plus minus T star times SE, which would be the 10.9. Now, if you're wondering, are we going to have to do stat key to get the T star on the test? No, it will be provided. Now, for the homework, you got to do it. And most likely, whenever you get to the quiz, to kind of prepare you for the feel of what's going to happen in the test, the quiz will also give you the T star. Just boom, do it, use it. We're going to get 4.31 and 17.49 as what they're, again, that's what they're asking for here. Do an interval that does the average increase on the CAOS exam after taking the class. The average increase is something between those two numbers. We are 95% confident that the average increase on the CAOS exam after taking the class is between 4.31 and 17.49. So the class does seem to be helping. Whenever students go take that multiple choice exam, they seem to do better afterwards. All right, but that is it. Again, that was focusing on matched pairs, where again the big main reason why you want to consider using that is when there's going to be variation from person to person, and not everyone's going to be experiencing the same amount of growth. Some of it might be a little, some a lot. Some might actually regress and go backwards in their performance or have no change at all. And I usually throw that in as like a true false question. Like, why would you consider doing matched pairs? Is whenever there's variation amongst, from case to case or from pairing to pairing. All right, but I'm going to go to another recording there. Hope this helps. Take care.